So this is going to be a little intro on the chi-square distribution. We're going to need this to try and find a confidence interval for sigma. What's sigma? Good, standard deviation. Which standard deviation? Yeah, it's the population standard deviation. So this is your population parameter. We want to find a confidence interval for that. It's going to rely on us understanding a little bit and using the chi-square distribution. So, okay, great. Just like all distributions, what's the total area underneath the distribution? 1. So here's a look at the chi-square distribution. The total area equals 1. So that's the only thing it's really going to have in common with our previous distributions of the normal distribution and the t distribution. Like the t distribution, it's going to changes with degrees of freedom. And I'll show you that change. Got a nice little Desmos presentation thing to show you how that shape changes. So it changes with degrees of freedom. So here's the chi-square distribution with 4 degrees of freedom, and then 5, and then 6, 7, 8, 9, 10, blah, blah, blah. And if you look at this distribution, as I increase the degrees of freedom, let me zoom out a little bit. As you increase the degrees of freedom, it starts to look more and more like a normal distribution, really. So that's interesting. It's not something that you should worry yourself about. The first and most important thing you should notice, though, is that it's not symmetric. In fact, where does our distribution start? Starts at 0. Our other distributions went from negative infinity to infinity. This one starts at 0. So it can't be symmetric, at least not with respect to the y-axis. So it's not symmetric. The areas underneath this curve are not things you want to do by hand. They are things that are built into the software that we're going to use, StatDisk. So let's see. Here's how you're going to construct your chi-square distribution, or chi-squared confidence intervals. So you're going to use this one down here. Now, this is a lot of work to try and find these values, chi-square sub r, chi-square sub l. So Cameron, your question from the last section kind of reminds me of what's going on here. These chi-squares sub r and chi-square sub l, that's going to be points in the right and left tails that have, a certain amount of area in them, and that area is going to be determined by alpha, our level of, our significance level. You're not really going to have to see that, but one thing I do want you to see is that this is no longer a nice symmetric interval. It's not like we was back in sections 7.1 and 7.2 where you did your estimate plus something and your estimate minus something. These are not nice and symmetric intervals. You have to do all this work with the square roots. That's to get an estimate for sigma. For sigma squared, by the way, what's sigma squared called? If this is your standard deviation, sigma squared is your? Yeah, your variance. Nice. So there's a lot of work with that, but fortunately for us, that's going to be done for us. Now there is one more thing that I want to point out about this, and that is something that's kind of essential. And that is this part right down here. You need a normal distribution to create this confidence interval. Now with our previous distributions, or with our previous sections, section 7.1 and 7.2, population proportion, population mean, if you didn't have normally distributed data to begin with, sometimes, actually oftentimes you'll be okay, but here it's very important. So let's remind ourselves how you can check whether or not something has a normal distribution. So check to see if your data is distributed. Distributed normally. No, that's a great question. It's not number 4. This is just different. In fact, this is going to be its own list. There was 3 things that we could do to check whether or not our data has a normal distribution. 3 kind of, rough and ready things you can do. I expect you to get 2 of them. So I don't remember what they would be. How can I check to see if my data has a normal distribution?
Symmetric.
All right, it's symmetric, and in particular, what about its symmetry? What kind of shape does it have to have?
Bell.
Yeah, it has to have a bell-shaped distribution. You can check that with a histogram. Look for a bell shape. I mean, certainly you can tell when it's not a bell shape. So that's one nice, easy way you can do this. What's the other thing? Had to do with that line. Remember what that was called? It was a normal quantile plot. You can get that if you do explore data off of StatDisk. And the last one that I've casually mentioned, but I'll mention again, is if there's more than one outlier, your data set's probably not normally distributed. If there is more than one outlier, the data is probably not normally distributed. Okay, great. That's an important assumption. I'm not always going to take the time to check those assumptions for us as we go through this. It just kind of slows things down a little too much. Let's do a couple examples from our handout. So I'm assuming and trusting that everyone got the handout from up front. We'll start with problem number 10. The Atkins weight loss program. Let me make this a little bit smaller. In a test of a weight loss program, 40 adults used the Atkins weight loss program. After 12 months, their mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. Construct a 90% confidence interval estimate of the standard deviation of weight loss for all subjects. Does the confidence interval give us information about the effectiveness of the diet? Well, let's write down a few relevant facts here and get rolling. This is problem number 10, or I'll call it example 10. Just to keep pace with our handout. And even though we're not going to use it, I'm going to write down a couple of these things. Like X bar was 2.1. N was 40. S was 4.8 pounds. And we want a 90% confidence interval. Okay, let's do this. Now, I'd be happier if at some point in this problem it said, assume the data come from a normally distributed population, which it should. Kind of a little bit surprised that it doesn't, but we have to make that assumption in order to do that test. If I want a confidence interval, and I'm going to do it on StatDisk, where do you think I'm going to go to find menu on confidence intervals? Which one of these? Analysis. Yes, analysis, confidence intervals.
Standard deviation, 1 sample.
Well, it's a good question. Is it standard deviation 1 sample or 2 samples? Do we have 1 sample of data or do we have 2 samples of data?
One.
We have just 1, right? So chapter 7 is going to be all about one samples. So one sample it is. We want a 90% confidence interval, so I got to change that to 0.90. I guess you don't need that trailing zero. Our sample size was 40. And our sample standard deviation was 4.8. This is the cool part. You get results in seconds. So nice. So our confidence interval is between 4.06 and 5.91. Okay. Justin, let me pick on you. What symbol should I put in there in the middle of my confidence interval? Mu was the last section. We were dealing with population mean. What's Chloe's?
Is it sigma?
Is it sigma? Does that sound better?
Sigma squared.
Yeah, sigma. It's always going to have to be a population parameter because that's the thing you're trying to estimate. So kind of a quick reminder here, going back to section 7.2, it's always going to be something like this because you're estimating population parameters. All right, let's see here. Let's state our conclusion in words. We can be 90% confident that the true standard deviation of weight loss, if you want to be really accurate, you can say on the Atkins diet, is between 4.06 and 5.91 pounds. There's a follow-up question to this. I'll give you a chance to copy that down. Question is, does this confidence interval tell you anything about the effectiveness of the Atkins diet?
Yeah.
It tells you how much the standard deviation could be, how much variability there is in the data. But if you're going to be on a weight loss program, do you want to know information about the standard deviation of the weight loss? Or is there something else you would want to know? If it works, and it works to be measured by not the standard deviation of the weight loss, but by the weight loss itself, right? So, yeah, you should be looking at X bar, not S or sigma. You should be looking at mu, not sigma. So this doesn't tell us much. But let me point out something kind of interesting and odd about this, and that is, here's our confidence interval, 4.06 to 5.91. But if you actually took a look at the standard deviation itself, it was 4.8. It's closer to here than it is to here. That's because your confidence interval is no longer nice and symmetric. So that's our best guess. That's our point estimate. But it's not in the middle of this interval. It's just not. It's just not the way the confidence intervals work for this one. Now, as far as judging the effectiveness of this interval doesn't really tell us much. You'd probably want to do a confidence interval for this, for the mean weight loss. We could do that real easily. That's just 7.2 kind of stuff. Let's just bang that out real quick. Confidence intervals, mean one sample, 90% confidence interval, Sample size was 40. Sample mean was 2.1. And sample standard deviation was 4.8. So, bam. There's your confidence interval. So, your mean weight loss would probably be somewhere between 0.82 pounds and 3.3, call it 3.38 pounds. That would tell you the effectiveness of this. Does that seem effective? After a year, you lose between a pound and 3.3 pounds?
Oh.
No, I'd be pretty unhappy on that. Very unhappy, because I think it's kind of expensive. So, if those numbers are actual numbers, then yeah, I'd be pretty unhappy.
Wouldn't the standard deviation being so high suggest that a decent amount of people actually gained weight?
Yeah, it does. It's exactly what it does. A significant amount of them probably gained some weight. And don't quote me on this, but I'm pretty sure that I remember Dr. Atkins himself died overweight, showing evidence of coronary artery disease. So, yeah, I'm not sure that I'd really recommend it, but you know, I'm not a medical doctor. I'm not going to dispense medical advice. All right, let's take a look at example 16. Right here. So you've got values listed below are waiting times in minutes of customers at Jefferson Valley Bank, where customers enter a single waiting line that feeds 3 teller windows. Construct a 95% confidence interval for the population standard deviation. And then you have the same kind of problem for the customers of the Bank of Providence, where they enter any of 3 lines that feed any of 3 teller windows, or that feed 3 teller windows. Now, I am going to just kind of do a little bit of this work here for you, because I got the data here, and I don't want to take the time and the time we have remaining to export that data and then plug it in for you. Let me just put that data into StatDisk. If you click StatDisk online in the upper left-hand corner, it'll take you back to your data editor. You can clear out everything there. And then I'm just going to paste in this data. There's something interesting about these data sets. I'm just going to call them Bank 1 and Bank 2. I normally don't like to do that, but we will for this case. The interesting thing is that the mean wait time for both of these different styles of banks, the mean wait time is 7.15 minutes. So, Bank 1, the mean wait time, X bar is 7.15. Bank 2, X bar is also 7.15. So obviously this data is contrived, but that's okay. I think it makes a good point, and it asks you to do a little bit of thinking when you're all done. We can run through and get confidence intervals for both of these banks. So if you were to do that, you'd end up with a confidence interval for Bank 1 for the standard deviation of 0.33 is less than sigma is less than 0.87. This is the standard deviation of their wait times. Let me see if you can kind of guess something first. Going back to the handout, or is it right here? Which bank, the first one or the second one, Jefferson Valley Bank or Bank of Providence, the data set from A or B, looks like it's probably going to have a bigger standard deviation?
B.
B. Why do you say B?
Data is more spread out.
Data is more spread out. Standard deviation reflects how spread out the data is. The data here is more spread out. So yeah, it looks like it's more spread out. It's going to have a larger standard deviation. That's actually reflected in the confidence interval. You have to wait. So the confidence interval in this case is between 1.3 and 3.3 minutes. Which one's better? Well, first of all, could these be the same? Could the standard deviations both be the same? No, they really couldn't. So you're right. The answer is no. Let's look at that on a number line. Over here you have 0.33 to 0.87, and then here you have 1.33 or 1.3 to 3.33. So for bank 1, we'll use orange. For bank 2, we'll use this very manly pink. There we go. There's no overlap between those two, is there? So it suggests that the banks have a different standard deviation of wait time. Even though they have the same mean wait time, they have a different standard deviation of wait time. Okay. So that's one of our conclusions here, is that the standard deviation of wait times is different. The second thing I want you to ask is, which one would you choose? If you were the bank manager, which experience are you going to give your customers? The first one or the second one?
Bank A.
Bank A? Good. Why is that, Keisha?
Because they more know what to like expect, rather than you would only
Yes.
spend 10 minutes.
Yeah. So what providing a smaller standard deviation is going to do is you're giving people a consistent experience. You know what to expect. It's about the same for everybody. I mean, if you take a look here, yeah, somebody got lucky and they went through at 6.5 minutes. You know, somebody was not so lucky, they went through at 7.7 minutes. Okay, so you're talking about a minute and 12-second difference between the two. Not bad. Over here, it kind of reminds me of being on the freeway and you see traffic backing up and you pick your lane, right? And it's like, oh man, I picked the wrong one because you're going so slow. You just hate that. You see everybody else in the next lane is going faster than you. You know, especially that annoying guy that was behind you. He gets through in the short lane, right? So with this method, there's a huge variation in this. Can you imagine how mad you'd be being this 10-minute customer watching somebody go by in 4 minutes? Yeah, you'd be pretty unhappy. So you want to give people a consistent experience, and that's measured by the standard deviation. So yeah, I think the manager would probably prefer to do it the way in Bank A, or in this case Jefferson Valley, as opposed to Bank B. You're giving people a more consistent experience so that, and I like the way you said it, they know what to expect. So, nice. Any other comments or questions on this one? All right, let me wrap this up and then I'll take attendance.